Hello friends, as we discussed in the previous lecture, physics includes the study of rotation. Arguably, the most important application of that physics is in the rolling motion of wheels and wheel-like objects. The physics and engineering of rolling have been around for so long that you might think no fresh ideas remain to be developed. However, skateboards and inline skates were invented and engineered fairly recently to become huge financial successes. Applying the physics of rolling can still lead to surprises and rewards. Our starting point in exploring that physics is to simplify rolling motion. Rolling as translation and rotation combined. Here we shall consider objects that roll smoothly along a surface, that is, the objects roll without slipping or bouncing on the surface. This figure here shows how complicated smooth rolling motion can be. Although the center of the object moves in a straight line parallel to the surface, a point on the rim certainly does not. However, we can study this motion by treating it as a combination of translation of the center of mass and rotation of the rest of the object around that center. To do this, pretend you are standing on a sidewalk watching the bicycle wheel as it rolls along a street. As shown, you see the center of mass O of the wheel move forward at constant speed v-com. The point P on the street where the wheel makes contact with the street surface also moves forward at speed v-com, so that P always remains directly below O. During a time interval t, you see both O and P move forward by a distance s. The bicycle rider sees the wheel rotate through an angle theta about the center of the wheel, with the point of the wheel that was touching the street at the beginning of t moving through arc length s. This equation here relates the arc length s to the rotation angle theta. R here is the radius of the wheel, the linear speed v-com of the center of the wheel, that is, the center of mass of this uniform wheel is ds upon dt. The angular speed omega of the wheel about its center is d theta upon dt. Thus, differentiating this equation with respect to time with r held constant gives us v-com is equal to omega r. This is the equation for smooth rolling motion. Now, these three figures show that the rolling motion of a wheel is a combination of purely translational and purely rotational motions. Figure A shows the purely rotational motion, as if the rotation axis through the center were stationary. Every point on the wheel rotates about the center with angular speed omega. Every point on the outside edge of the wheel has linear speed v-com. Figure B shows the purely translational motion, as if the wheel did not rotate at all. Every point on the wheel moves to the right with speed v-com. The combination of figures B and A yield the actual rolling motion of the wheel shown in figure C. Note that in this combination of motions, the portion of the wheel at the bottom, that is at point P, is stationary, and the portion at the top, that is at point T, is moving at speed 2 v-com, faster than any other portion of the wheel. These results are demonstrated in this figure, which is the time exposure of a rolling bicycle wheel. You can tell that the wheel is moving faster near its top than near its bottom because the spokes are more blurred at the top than at the bottom. The motion of any round body rolling smoothly over a surface can be separated into purely rotational and purely translation motions, as in figures A and B. Friction and rolling. If a wheel rolls at constant speed, it has no tendency to slide at the point of contact P, and thus no frictional force acts there. However, if a net force acts on the rolling wheel to speed it up or to slow it, then that net force causes acceleration ACOM of the center of mass along the direction of travel. It also causes the wheel to rotate faster or slower, which means it causes an angular acceleration alpha. These accelerations tend to make the wheel slide at P. Thus, a frictional force must act on the wheel at P to oppose that tendency. If the wheel does not slide, the force is a static frictional force Fs and the motion is smooth rolling. We can then relate the magnitudes of the linear acceleration ACOM and the acceleration alpha by differentiating Vcom is equal to omega r with respect to time, with r held constant. On the left side, dVcom upon dt is ACOM, and on the right side, d omega upon dt is alpha. So, for smooth rolling, we have ACOM is equal to alpha r. If the wheel does slide when the net force acts on it, the frictional force that acts at P is a kinetic frictional force Fk. The motion then is not smooth rolling, and the equation ACOM is equal to alpha r does not apply to this motion. This figure here shows an example in which a wheel is being made to rotate faster while rolling to the right along a flat surface, as on a bicycle at the start of a race. The faster rotation tends to make the bottom of the wheel slide to the left at point P. A frictional force at P directed to the right opposes this tendency to slide. If the wheel does not slide, that frictional force is a static frictional force. The motion is smooth rolling, and the equation ACOM is equal to alpha r applies to this motion. If the wheel were made to rotate slower on a slowing bicycle, we would change the figure in two ways. The directions of the center of mass acceleration and the frictional force at point P would now be to the left. Rolling down a ramp. The figure here shows a round uniform body of mass m and radius r rolling smoothly down a ramp at angle theta along an x-axis. We want to find an expression for the body's acceleration down the ramp. We do this by using Newton's second law in both its linear version and its angular version. We start by taking into consideration the different forces on the body. First, the gravitational force Fg on the body is directed downward. The tail of the vector is placed at the center of mass of the body. The component along the ramp is Fg sin theta, which is equal to mg sin theta. A normal force Fn is perpendicular to the ramp. It acts at the point of contact P, but in figure the vector has been shifted along its direction until its tail is at the body's center of mass. A static frictional force Fs acts at the point of contact P and is directed up the ramp. We can now write Newton's second law for components along the x-axis as Fs minus mg sin theta is equal to MACOM x. This equation contains two unknowns, Fs and ACOM x. We should not assume that Fs is at its maximum value, Fs maximum. All we know is that the value of Fs is just right for the body to roll smoothly down the ramp without sliding. We now need to apply Newton's second law in angular form to the body's rotation about its center of mass. For this, we shall first use torque equation tau is equal to r perpendicular into F, derived in earlier lecture, to write the torques on the body about that point. The frictional force Fs has momentum arm r and thus produces a torque Rfs, which is positive because it tends to rotate the body counterclockwise. Forces Fg and Fn have zero momentum arm about the center of mass and thus produce zero torques. So, we can write the angular form of Newton's second law, that is tau net is equal to I into alpha about an axis through the body's center of mass as Rfs is equal to ICOM into alpha. This equation contains two unknowns, Fs and alpha. Because the body is rolling smoothly, we can use equation ACOM is equal to alpha r to relate the unknowns ACOM and alpha. But we must be cautious because here ACOM x is negative, that is in the negative direction of the x axis, and alpha is positive, that is counterclockwise. Thus, we substitute minus ACOM x upon r for alpha in angular form of Newton's second law. Then, solving for Fs, we obtain Fs is equal to minus ICOM into ACOM x upon r square. Substituting the value of Fs in Newton's second law equation, Fs minus mg sin theta is equal to MACOM x for components along the x axis, we get ACOM x is equal to g sin theta upon 1 plus ICOM divided by mr square. We can use this equation to find the linear acceleration ACOM x of any body rolling along an incline of angle theta with the horizontal. Looped slip string or a yo-yo. As shown here, a looped slip string, commonly called a yo-yo, is a physics lab that you can fit in your pocket. If a yo-yo rolls down its string for a distance h, it loses potential energy in amount mgh, but gains kinetic energy in both translational and rotational forms. As it climbs back, it loses kinetic energy and regains potential energy. In a modern yo-yo, the string is not tied to the axle but is looped around it. When the yo-yo hits the bottom of its string, an upward force on the axle from the string stops the descent. The yo-yo then spins, axle inside loop, with only rotational kinetic energy. The yo-yo keeps spinning. We can call this state as sleeping until you wake it by jerking on the string, causing the string to catch on the axle and the yo-yo to climb back. To find an expression for the linear acceleration ACOM of the yo-yo rolling down a string, we could use Newton's second law just as we did for the body rolling down a ramp. The analysis is the same except for the following. Instead of rolling down a ramp at angle theta with the horizontal, the yo-yo rolls down a string at angle theta is equal to 90 degrees with the horizontal. Instead of rolling on its outer surface at a radius r, the yo-yo rolls on an axle of a radius r0. Instead of being slowed by frictional force Fs, the yo-yo is slowed by the force T on it from the string. The analysis would again lead us to the linear acceleration equation a x is equal to g sin theta upon 1 plus I divided by mr square. Therefore, let us just change the notation in equation and set theta is equal to 90 degrees to write the linear acceleration as a is equal to minus g upon 1 plus I divided by mr square. Here I is the yo-yo's rotational inertia about its center and m is its mass. The yo-yo has the same downward acceleration when it is climbing back up. Torque. In the earlier lecture, we defined torque for a rigid body that can rotate around a fixed axis with each particle in the body forced to move in a path that is a circle centered on that axis. We now expand the definition of torque to apply it to an individual particle that moves along any path relative to a fixed point rather than a fixed axis. The path need no longer to be a circle, and we must write the torque as a vector that may have any direction. Figure here shows such a particle at point A in an xy plane. A single force F in that plane acts on the particle, and the particle's position relative to the origin O is given by the position vector r. The torque acting on the particle relative to the fixed point O is a vector quantity defined as tau is equal to r into F. We can evaluate the vector product in this definition of torque by using the rules for vector multiplication. To find the direction of torque, we slide the vector F without changing its direction until its tail is at the origin O, so that the two vectors in the vector product are tail to tail. We then use the right hand rule for vector products, sweeping the fingers of the right hand from R, the first vector in the product, into F, the second vector. The outstretched right thumb then gives the direction of torque. In figure B, the direction of torque is in the positive direction of the z axis. To determine the magnitude of torque, we apply the general result of equation C is equal to AB sin phi, finding tau is equal to RF sin phi. Here phi is the smaller angle between the directions of R and F when the vectors are tail to tail. So friends, here we come to the end of our discussion in this lecture, and therefore we sum up. For a wheel of radius r rolling smoothly, Vcom is equal to omega r, where Vcom is the linear speed of the wheel's center of mass and omega is the angular speed of the wheel about its center. The wheel may also be viewed as rotating instantaneously about the point P of the road that is in contact with the wheel. The angular speed of the wheel about this point is the same as the angular speed of the wheel about its center. If the wheel is being accelerated but is still rolling smoothly, the acceleration of the center of mass is related to the angular acceleration about the center. In 3 dimensions, torque is a vector quantity defined relative to a fixed point, usually an origin. So that is it for today. In the next lecture, we shall be talking about angular momentum. Thank you very much.